anche riepilogata, non so dove. So, switching to English. Today we will be mostly doing practical thing, but as I had this question, why, or can you show me why the partial autocorrelation function ARP process vanishes after the pth delay? This is pretty simple because if you see the partial correlation this way, so for example, we have the YT, so our time series is YT, and we suppose it's standardized, okay? So it's mean 0, variance 1, okay? Then if it means 0, I can just omit also the intercept, whatever. So the model is telling me this story. And the partial autocorrelation, you can think it as if it's the P, if it's a regression of YT. So suppose we're interested in H lags. So the H lag auto correlation, auto covariance function, of course, when it's 0 to 1, it's also 0. So if we regress, we can use alpha because we use that in the definition. We can do this regression. Actually, let's call it a slightly different naming. Let's call B1, B2, then beta or beta H minus 1. And then the last one we call alpha H. Okay, I'm just changing the name of the last one. Okay, because this is going to be. So I'm doing this regression. Okay. So this is going to be proportional to the partial autocorrelation function. Okay. To the autocorrelation at the partial autocorrelation at lag H. Okay. So this is another way to define this with the autocorrelation at lag H. Okay. So I do this regression. Of course, what happens if H is larger than P, then in population, this last coefficient is 0. Okay. Because it's, I mean, if it's larger, there's nothing more here. Okay. So this is the model that is generating the data. And suppose that H is larger than P. Well, then T minus P will be somewhere here. I don't know. Maybe I should add another, just to be more explicit. Here's beta P times T minus P, and then it goes on. Okay. And of course, yeah, okay, we can also leave just to let you understand how things are going. So this is beta H minus 1. Okay. So if I do this estimation, of course, this beta will be different than 0. Okay. But the other ones, they're all going to be 0 because there's nothing here more than this delay. So the highest lag, which is in my model, is P. So if I regress on more than P lags, of course, all these coefficients are 0 in the population, and from a sample point of view, will be very close to 0. There will be not exactly 0, that will be close to 0, and probably not significant. Is that right? So this is another way to find out the partial covariance. And if I have to I have to remind that probably if this is standardized, as I mentioned, this is exactly the autocorrelation, the partial autocorrelation.
Maybe sensitive
Hmm?
from the mean.
It's already sensitive. If it's standardized, it's sensitive on the mean.
Yeah.
It's probably it's either the auto, yeah, I think it's just the autocorrelation. This is standardized. Okay. Actually, even if it's not standardized. But anyway, if it's not there, it's just proportional. I have to check it. For some reason, I'm not reasoning about that I'm not be reasoning about that for a long time. But anyway, either if it's the correlation or just proportional to the correlation, doesn't change much. And anyway, this is the partial autocorrelation or proportional to the partial autocorrelation. This is going to be 0 for h that is larger than p. Of course, if h is smaller than p, it will not be exactly phi because of all these regressors, which are delays of the same variable, are correlated. And as you probably know, as soon as you add correlated regressor, all the coefficients of the regression change. Okay, so if the regressor are orthogonal, so they are not correlated with each other, it doesn't matter if you add another regressor, the coefficients of the other regressor will not change. But if the regressors, as in this case, because it's a time series, are correlated, then every time you add a regressor, all the other regression coefficients are going to change. Okay? So that's why this is not, I mean, if you put everything in this way, this is going to be like this one. But if you have h instead smaller than p, then you're doing a regression on less variables than here. And as these are correlated, the coefficient will be not coincident. Okay. So there's a slight difference in the phi and in the partial autocorrelation coefficient. Okay, they are not exactly the same number, but what we see is that it's easy to see that after t minus p, all of these they are zero because this is the data generating process, so the ARP, and these are in excess. They're not there. Okay, so this is like an intuitive way to see why the partial autocorrelation function on ARP is going to 0 after p lags. Okay, so that's the simplest way to prove it, sort of simply, without going into deep into math. But it's, I mean, it's very intuitive. Also, you can also prove it using the projection, the linear projection properties.
Seen many different ways demonstrate the same things, but say none of them was to, let's say, to reduce enough in the sense of mathematically speaking.
Yeah, I mean, I can provide you proof using, I mean, using the linear projection properties. It becomes also very easy.
I think that in the MA case is more intuitive to see the fact that even mathematically speaking, the fact that the HCF tends to see. Well, in that case, when studying it some days ago, I had a bit of confusion improving it.
Yeah, I'll give you a proof. Yeah, a proof based on the P operator, just exploiting its properties, and you will see it's pretty simple in that terms. Yeah. Yeah, well, just because the conditional covariance goes to 0, I'll give you that. I'll write it down maybe in a R markdown, which is simpler. So today, what I wanted to do is taking a time series which is not that simple as the ones we have seen. We just worked with quarterly and monthly time series, which are usually pretty easy to deal with using ARIMA models because they only have one seasonal periodicity. And let's move to more involve time series. One of these time series I put on the e-learning, which is here, for your, let's say, contest or project, whatever you want to call it. So these are the rules. So it's a hourly time series. It's just the count of number of people going into an Australian street. I will be not precise than that because I don't want you to look at the original data, because of course there's a part I put to missing the last part of the time series, which is the part of the time series you have to forecast. Okay, so so it's a count of number of people passing in front of a sensor which is installed in a street in one city in Australia. And it's pretty long time series. I think it starts from 2009. And so the time series you have goes up to 2020. And okay, you have no missing data until the last day of 2019. And then you have missing data starting for the first day of 2020 until I think either February or March, I don't remember. I just wanted to avoid COVID because, of course, making prediction of people going around during COVID is complex. I don't think in Australia they had any restrictions. Of course, in April they had restrictions, probably not in March. But anyway, I checked, and so you will see that the time series ends before the COVID starts. Anyway, so the last 1,440 observation, because it's a hourly time series, are missing. So you have the date and the time, and you have the time series, and then you have missing observations. And what you have to hand in, like at least one day before the examination, is a CSV with the prediction for that 1,440 observation that are missing, and you have to provide the prediction using ARIMA, one prediction using unobserved component models, which we're going to start, I think, next week. And also one of the machine learning, you will be trying more than one machine learning algorithm. Then you pick the one that you think is working the best, and then you just submit the best machine learning algorithm, okay? So you have a submission with the data is already there, a prediction done using ARIMA, a prediction done using UCM, and a prediction done using machine learning, okay? So that's basically your project, hackathon, contest, whatever you want to call it. And you can already start because we are going to end the part on ARIMA modeling, maybe today, maybe if it's not finished yet, maybe Monday, but it's almost finished. And probably just today we are going to finish that. And so you can already start do some consideration and try to fit the ARIMA model. Okay, the prediction will be evaluated. I chose the mean absolute forecast error, which is usually what you don't minimize. Usually you minimize the mean square error, but anyway, I chose to, I mean, usually they will tell you a very similar story. But anyway, this is the metric I will be used to do the ranking of your predictions. And the ranking will be, the ranking is more, again, it's really not something I will be using for your final grade, but the ranking will be based on, there will be one ranking for your best model. So I pick the best model that everybody has submitted. And based on that, there is the ranking with all your colleagues. But then there will be a ranking just for the ARIMA models, then for the UCM models, and for the machine learning models. Just to show you how well you did in that. And then, of course, forecasts are partially due to a good modeling that you did, and partially due to luck. That's why it's not I mean, it's not going to influence your grade anyway, but you have to do that. Or as I mentioned last time, you can also propose your own time series, and I can tell you, okay, you can analyze that time series, fine. And in that case, you will be presenting that. And while if you pick up this, you will present in what you did for forecasting this time series using the three methods. And then, of course, you also have the ranking, which is more again than seriously, okay? And the time series is here. The idea today is we pick up an hourly time series, which is, for example, the one they loaded on the e-learning ElectroQuant. So you should download, if you haven't yet, this ElectroQuant CSV. So that's the quantity of electricity exchanged in the day-ahead market in Italy. So I have it somewhere already. Actually, I can. So download it wherever you can reach it. And then let's just load the data. Okay, I will call it just DT, like data. It's a CSV. Oops, CSV. Okay. So I need some time to do that because I'd like you to kind of reproduce what we're going to do and also to get involved on some of the reasoning about this time series. So let's check it. So this time series is actually, it's called, this is the, yeah, it's called load because the demand, actually is the demand and the offer of energy on the day-ahead electricity market, because of course demand and offer have to match, okay? So this is the quantity, let's say, of electricity exchanged in the Italian day-ahead market. As I probably mentioned to you, in most of the countries where the electricity market is liberalized, things work this way. The one day before delivery, so today for tomorrow, there's going to be 24 auctions, and in these auctions, every producer will submit their offer to sell, and every buyer will submit the offer to buy. So the quantity and the price, and of course, the demand curve and the offer curve will cross, and that will be the equilibrium price and quantity on the day-ahead market. And we have 24 prices because there are 24 hours of the day. So today there are 24 options for the 24 hours of the day of tomorrow, okay? And this is a very liquid market. I would say in Italy, I would say between 70 and 80% of the whole electricity goes through this market. Okay? So it's important to be able to predict that. And then, of course, after this market, there are some other markets. There are some that are very similar to this one, are just like adjustment to this market. And then there is like a final market, which is a market to always keep the grid in balance. So it's called balancing market indeed, because of course the quantity of the real quantity of electricity which is demanded by the consumers or the industries changes every minute, and so the one that runs the grid, which in Italy it's called Terna, has to adjust the quantity produced according to the quantity demand. because they have to be constantly in equilibrium. You cannot have a higher production than the requested quantity, and you cannot have a higher requested quantity than production. Otherwise, the system fails. Okay, and so there is like a continuous time adjustment to the demand, and that, of course, is done using other type of auctions and using just some pivotal power plants around Italy. But this is already a very important number. It's going to be very close to the real number of tomorrow. So it's an hourly time series. We have the date. So you see this one starts from 2016, January, and it ends on like 31st May 2024. Actually, you can download the latest of this on mercatoelettrico.org, which is the official site. So anyway, and you can also download a lot of more data there. If you're interested in the electricity market, there's plenty of data over there. Also of the single auctions, okay, not just of the equilibrium price, but every auction has all the data available. And under that aspect, where in Italy we're the most transparent market in the world. There's no other market where all the data we can download from there get published. We know the offer of every single plant in Italy, with the name of the owner of the plant, so the company that owns the plant. So our data, the Italian data about electricity markets, are maybe the most transparent in the world, and you can download them pretty, I say pretty easily. If you can ask for FTP access, otherwise you have to download the auction data day by day, which is very time consuming, of course. But instead of the equilibrium quantity and the equilibrium price, you can already download it as Excel files. So that's much easier. But anyway, so this is the time series we want to analyze and eventually predict. So first of all, let's suppose we're just facing these numbers. What would you do first?
Let's plot that.
Of course, plotting. Why not? Yeah, we should fix something. Okay, we don't have just one variable, both for the date and for the hour. We could make that. Or maybe for the moment we just look at the data and I don't care about that. Anyway, if we want to, for example, to put just one variable with the whole date, so the date time in the same way, we could do that using I would call straight away actually I would call the tidyverse. Do you know the tidyverse work a little bit? Well, I can explain to you while we are doing things. Of course, that's a very handy set of functions to work with data. It's kind of SQL oriented. So if you know SQL, you will find yourself very fine in this world. And of course, then we have also like ggplot inside, which does excellent graphics, and lubridate, which is great for working with dates. Actually, what I call the tidyverse is not a package, it's just a selection of packages. Okay? So these are all the packages that were loaded by just loading tidyverse. So we have, this is for working SQL-like on data frames. This is for categorical variables. We're not going to use that much here. ggplot2 is the main, I would say, the most beautiful way to produce graphics in R. Lubridate is, as I told you, a very large set of functions to work with dates, and of course we can use that to produce better dating here. And well, this per with 3 R's it's a set of functions to work do you know the apply functions? You know the kind of apply function. Apply function usually work with just one set of, I don't know, you can have one matrix or an array of matrices or a list, and the apply class of function will work on every column or every row or every third dimension of the array or every single entry in a list. It's like a generalization of those functions to work with more than just one of these objects. Like if you want to parallelly work on more, we're not going to use that, but just to inform you about the set of functions. So reader is just a more complete version of the CSV, read CSV. I think there's just a couple of functions here. Read CSV works pretty fine. Sometimes you may want to have something more flexible, so you have it here. Actually, it's also implemented in RStudio up there. If you go with import dataset, you have the standard reader, read CSV, or you have also the one which is contained here. Stringer is a set of functions to work with string. Table is just like a data frame, but in this world, usually what you produce, it's called table. Probably it's got some features that are needed to, I don't know, speed up things here. So the table is just like a data frame. A name for this. And I think the class table is just an extension of the class data frame. Entidier is another set of functions to reshape data sets. Okay, we will be using, for example, in this example, a function called pivot wider, which is made to convert like a very long data set like this one in a larger one. And I'll tell you why. So this is basically what this loads automatically. So I just load all of them. This is something you should be acquainted with while using R. While in Python, you always have to, probably I already mentioned this, you always have to say from which package are you using what function. Of course, if are not function of the base distribution of Python. So in Python, if you have like an ARIMA function, you always have to tell from what package this ARIMA function is to be taken. In R, you know, you can work that way using the semicolon, or you can load the package. Of course, if loading the package finds another function which has the same name of the function, one of the functions you are loading, then there are conflicts, and the last loaded function will mask the previously available ones. But everything is made clear here, okay? So filter, of course, filter here is used like a where in SQL. But of course, we have been using the stats filter for a while. It's just got the same name. We didn't lose this, but now in order to call this function, we have to be explicit and say, okay, stats, semicolon, filter, okay? And the same thing is lag, which is very good because the lag function in stats is a terrible function. So it's good that somebody rewrote it in a proper way. So. And that's it. So, for example, let's maybe, I don't know, build a working data set, working data. Actually, if you want to be more coherent, we can go from the left to the right. Okay, this is I don't know if you ever used, this is the pipe which belongs to this world, and this is the pipe that then they added to R. So R didn't have any pipe until version 4. Started from version 4 because the pipe of the tidyverse world was very popular, and then they added this pipe to the basic R package, okay? So you can actually use both now. Before version 4, you just had this one. So whatever you want to use it, okay? They have slight differences, but I think we will not use any of this difference. So whatever you want to do, you use it. So this, of course, take this data set and pass it to whatever function. So the first thing we want to do is create a new variable which has both the date and the hour inside the same field. And in order to make new variables, there's the function mutate. So mutate in the tidyverse word means create a new field or a new variable, okay? And the simpler way to use it is like new name. We could call it datetime. And then use a function. For example, there is, as I told you, inside LoopRedate, there's a bunch of functions to work with data. In this case, I would bet there is a function called year, month, day, and here you have the proposal, and hour. So this is to build a date from year, month, date. This is to build a date from, or a date time from year, month, date, and hour, then hour minutes, and then hour minutes seconds. So these are all possible formats. So what we have to provide here is a string with the dates in this format. And we can do that by pasting the date with the hour. Oops.
What's the difference between paste and paste 0?
Okay, paste always puts a separation. Actually, here should be paste, not paste 0. So paste 0 doesn't put any separation between the strings you are going to paste together. Paste is going to put a separation with, by default, is a blank space, but you can change it with a sep arguments. So it's paste 0 is like paste with sep equal to the empty string. Okay. But actually here we have to use paste because we need a space between the two. So we have like the date. The date is, you see, it's just a number, but it gets converted into a string when you go with paste. And so we have like year, month, day, all in a row. But I think this function is intelligent enough to understand that, even if there is no like minus sign between the parts of the date, and then space and the hour. I think it's going to work. And then we can assign that to a new data set, which we will call like working data. I don't know. Okay, you see there are some problems. It says there are some like 8 cases in where it fails to parse. What does it mean? That it cannot convert that string into a date. So the nice thing is that you probably have not noticed, but we have 8 years of data. So that happens 8 times, once in a year. And let's see when this happens. You have any clue why this is happening? So let's go to October. I think we will find that in October. So this is already December. Sorry, I opened the wrong one. Okay, here's in October. Let's go towards the end of October. This is something you should be prepared of because it's something that is common to many time series. Um, okay, maybe it's I'm quicker if I just tell you why. So this is the problem. You see it already from here. Is there anything strange here? It goes from 1 to 25. Okay. Yeah, it's October. Okay, it was really late in October. So what's the problem here? Yeah, the daytime. So sometimes it happens that when you have this change of time, dates are like you have longer date of 25 hours, and then you have a day with just 23 hours. Okay. And is there a problem? Well, yeah, it's kind of a problem because well, we already see we cannot even define the date in that case. What about how do we work with these data? Well, you have to reason a little bit about the meaning of this data. I mean, when we change the time, we just straight away change our habits to the new time. So actually, it just like the new, I don't know, 8 in the morning are just like the old 8 in the morning. So what I usually do when this happens in this time series where, okay, the changes in the night where nothing interesting happens as far as electricity demand is, I usually just delete the 25th hour and I duplicate the 23rd hour when the 24th hour is missing, okay? So that could be a good way to do that, okay? So do you have a suggestion? What's the best way to, okay, we don't have a list. We could have a list of the day in which the change happens. I mean, it's very simple to just leave out the 25th hours because we can use the filter function, for example, and just throw that away. The problem, how do I find the missing 24 hours? So, for example, if we filter before creating the variable, so if we filter saying select hour less than 25, and then I pass this to the next function. So this is going to solve the problem with the 25th hour, okay? So now we will not get any warning or whatever. So this worked. The problem is that when this happens, you always have to keep in mind, well, then there is the date in March. It's of course in March. It's the last weekend in March in which the 23rd hour is missing. We can either we can work in two different ways. We can either identify what day is that. So it's not complicated. It's the last Sunday of March. Or since I want to work in two different ways for this prediction, I want to work on the 24 hours time series, but I also want to work on 24 daily time series. So I have two alternatives when I have hourly data. In some way, working with 24 time series, which are daily, one for each hour, is much simpler. Of course, I have to produce many more models. I have to produce 24 models instead of just one, but these models are much easier to manage. And as far as forecasting, of course, probably these models, so the models based on daily data instead of hourly data, will lose some forecasting power for very short predictions, like 1 hour ahead, 2 hours ahead, 3 hours ahead. But usually, for example, for this time series, I'm really not interested in predicting few hours ahead because I always have to predict at least 1 day ahead because this option I mean, today I'm going to play in the auction for tomorrow data. And so the tomorrow data will be available all together, I don't know, at the end of the day. So it's really not interesting to predict 1 hour ahead. It's not useful for me as a business, for example, to submit my offer or bid of quantity request. So usually very short-term prediction are really not taught. And sometimes you don't learn so much from the short term as much as you earn from the long term if you work on daily data. So we'll be working on this time series, but we'll also be working on 24 different time series. Of course, we will be working on one, and then the other 23 will be similar in some way. So anyway, even before doing these things, let's just plot the data. Of course, we will have a jump once in a year, but it doesn't really matter, just for the plot. So we call ggplot. I don't know if you're acquainted with that. So we need the aesthetics. The aesthetics are the variable. They're mapped to objects in the plot. So the x-axis will be the date or the date time. The y-axis will be the load variable, okay? And then we have to pick up the type of geometry that we want to see in the plot, and that's geom, and we want a line. And so this is basically how the ggplot works, okay? Also, ggplot has thousands of, sorry, a mistakes that you will always make, as I do probably, is that ggplot works with plus, not with pipes, okay? So once you start defining the plot, all the various parts of the plot are connected by a plus. ggplot is also kind of slow because it makes nice plots, but it may be pretty much involved. Anyway, well, this takes some time because it's full of data. So actually, as you suggested, looking at the plot here, it doesn't suggest too much to me. What we see in general is that there is a slight trend that goes toward less consumption, maybe slight. Well, of course, we have the COVID time here, clear. It's very clear. We see there is some kind of seasonality within the year, because, for example, we see that there are two negative peaks. We already saw that on my application, my Shiny app, about the sinusoids. We kind of have two negative peaks. One is around the change of the year because of the winter vacation, and one is in August. Here it's hard to say which is which, but anyway, like probably, I don't know, one is, this is, I don't know, this is probably winter vacation, this is August, okay? So anyway, we have some repetitions during the year. But maybe more interestingly than that, we can just look at a shorter part of this time series, so a shorter lag, a shorter time period. So we can like filter. Now let's just look at maybe a couple of months. So we can this starts from 2016. Maybe we can just take the first 2 months or the first 3 months of 2016. So we can just say, well, we also have the date. So we can say date less than 2016, March 30. And then do the same plot. Just copy here. Okay. These are about 3 months of data. Let's see some features and consideration of this time series. Okay, we see straight away this is probably due to the winter vacation. Okay, it starts with a very low demand that goes up probably around the 6th of January. If it's not a weekend, it's going to go after the 6th. So that's starting from the 7th of January, it starts to go back to the normal consumption. Then we clearly see there is like a 24 hours pattern. Every day we see there is a peak during the day and a negative peak during the night. You see so this is about 24 hours. Every extremes is after 24 hours, okay? So this is like probably night, and the positive peak is probably, I don't know, around 9 in the morning or something like that. You can check that. But then these peaks are different. This is probably Saturday, and this is probably Sunday, okay? So you have 5 days, so Monday, Tuesday, Wednesday, Thursday, and Friday. Then you have Saturday and Sunday, and start over, okay? So just by looking at this time series, we are noticed there is probably a within year seasonal pattern with negative values, negative peaks on the change of the year in August. Then there is a 7 days seasonal component, because especially Saturday and Sunday are different, but probably if you look at that, maybe also Friday has a slightly different behavior. But most of all, Saturday and Sunday, they behave very differently than the other days. And if you look at the single day, you see one day, a 24-hour pattern, okay? So it's just like 3 seasonal components, one above of the other one, okay? So we have three seasonal components. And that makes things complicated, but we can find ways to manage them, okay? What makes it even more complicated is that this seasonal component, or at least the 24 hours seasonal component, interact with the other ones. Because of course, the shape during the day is different on the weekend. And the shape during the day is different in summer with respect to winter. For example, we can make an even smaller. So let's just look at, let's just take March, maybe. Okay. So this is just 1 month. We clearly see now, actually during the day, there are 2 peaks, one in the morning and one in the evening. The peaks are very different, or I mean, the whole shape is very different on Saturday and even more different on Sunday. I mean, the 2 peaks are still there, but the difference between the top and the bottom is much larger, seems like. And then, of course, it goes on. And here, what do you think this is? I mean, we see something strange here. What do you think this is? This is probably Easter. We can check when Easter was on 2016. I would say around the 28th of March, we can check. Yeah, the 27th of March. So we have like probably so Saturday, Sunday, this is Monday, Pasquetta. And probably the whole week here could be somewhat smaller in numbers because of many that do the week, Easter week vacation. Okay. So it's not that simple. As I told you, we could, I mean, if we want to work on hourly data, we have to take into account 3 different seasonal patterns. And we should actually also take into account seasonal patterns that interact, okay, which make it even more difficult. Because it's mostly the 24-hour shape that changes within the year, okay? But as I told you, we have also this alternative. Instead of working on one long time series, we can work on 24 shorter time series or 24 daily time series. And in that case, I get rid of the problem of managing the 24-hour seasonality. That is taken account automatically by the fact that we are building different models for different times of the day. So maybe we can start from this second version, which is a little bit simpler. But we can also exploit the fact that we're going to build like a data set with 24 time series, daily time series, to spot the moments in which there are missing values on the 24th hour, and then fill it up probably just with the last value available, and then build back the hourly time series with no missing observations. Anyway, so how how can we build the 24 time series? Maybe we can call it I don't know, the T24. But let's go the other way around. So starting from this one, actually we could start from the original one, because in this case we're not needing the daytime. So let's start from the original data. In order to make a database which is long, so in some way the data set we have is tidy, meaning that it's really long. A tidy data are according to the definition of the guy that wrote all these packages and made this definition clear. And this definition was very powerful because now everybody's talking about tidy data, tidy approach, even in Python. I mean, it starts from R because this guy called Wickham Hadley, which is it kind of revolutionized a little bit R as far as data analysis is concerned. Made some definition there now pretty much used everywhere. So his mind, a tidy data is something that is as long as possible putting the same type of variable in the same column, okay, and then using different names to say, okay, this is that kind of number, okay. But of course, here in time series analysis, sometimes we want a time series to be, every time series to be in a different column, in a different field. And so there is this pivot wider function, which belongs to tidier package, where we can say we want names from, so our names will be the hour, and values from, and the values are from load. Now, what happens is this will build for every single hour a name of a new variable, and the value will be taken from load, okay? The problem is that hour is a number, so we don't want the name of a variable to be a number. We could, I mean, it's not forbidden in R. You can also have column name after number, but maybe just to be able to call the variables in a simpler way without using apostrophe or something like that. We can, but there is like prefix. I think it's called prefix, but anyway. It's called names prefix. Names. And I would put an H before the name, so like hour number 1, hour number 2, and so on. And that, as we said, we can load, we can store that into like a DT24 data set. Okay. Yep.
Just to better understand.
Yes.
The
what?
The idea is we are facing a problem in which the kind of seasonality appear in different way. Let's say
3 seasonal patterns, and probably one of those, at least one, changes according to the other one.
Okay, so we are trying to split the problem according to.
Yeah, one way to make this a complex problem simple in this way is, instead of doing one single model that accounts for every possible seasonality and interaction between the seasonalities.
At the end of the day, what we are going to do, an ensemble of the 3 different approaches, because
no, it's not an ensemble. It will be, we have a model to predict the first hour, we have a model to predict the second hour, and so on.
Okay.
So we have 24 models.
Okay, so depending on our need, we use one of them.
I mean, that's a solution. That's a solution that kind of works because makes our work simpler, and in some way lets every single model take care of the fact that within the year, hour 5 and hour 7 will change in a different way in some way. So I make the models more independent. As I mentioned before, you may say, okay, but if you build daily models, say, well, hourly models, probably I'm always using, for example, if I'm predicting hour 10, I'm using not only the information up to hour 9 of the same day, but I'm using the information up to hour 10 of the last day. So I'm not using the newest information available. That's right. But of course, if you had to predict 1 hour ahead or 2 hours ahead and so on, probably that information would be very relevant. And so this wouldn't be a good suggestion, okay? But usually we are not interested in doing, for example, for this real application here, for this real application, our interest is not in 1 hour ahead forecasting, but at least 1 day ahead forecasting. Because if I want to, for example, the model to be useful for a firm like Enel that has to bid on this auction, then today before 5 o'clock, I need the prediction of the whole 24 hours of tomorrow. So I'm not interested in predicting 6 o'clock based on information up to 5 o'clock because it's useless.
But maybe it's not the context, but if we need to predict 1 month ahead.
Yeah, for 1 month ahead, I would say then this the latest information is really not that important. I mean, if you have to predict 1 month ahead, then go with daily data.
Okay.
Yeah.
So there are situations in which, depending on your task or objective, you use monthly, or you are creating.
For if you need a model where you have real-time data and you need to predict I don't know, moments ahead, whatever the frequency of observation is, then in real-time situation, then it's good that you're using every single observation until the last one. But in this case is not that case. So, but I didn't tell you that we don't do that. We will try to do that. I mean, modeling also the hourly data, okay? But it's more complex. So let's start with a simpler way, and then let's move to the more complex way. And of course, we can then compare the prediction made by the 24 models. Of course, we don't have time to produce 24 models. So maybe we can just find one model and then fit the same model for all the 24 observations. But then we can see what happens if we predict like 1 month ahead and see which of the two models is working, okay? I don't know in advance which it will be, but probably the daily one will beat the hourly one if we're predicting up to, like, in this case, I told you 1 month ahead. Yeah, 1 month ahead. I'm pretty positive about the fact that the daily models will beat the hourly. On very short-term prediction, the hourly model will beat the hourly, okay? Anyway, so now we created this 24, actually 25 hours. If you look at here, we have, you know, the date, and now we have the hours up here, and we worked with the original ones, and we have 25 hours indeed. But of course, there's only 1/25th hour per year in October. So, but this is nice because we can also easily get the moments in which the 24th hour is missing, which will be March here, for example. So this is the 24 hour which is missing, and it's surely in March. So it's the 27th of March, because it's the last Sunday of March. Okay? So we can use this format to simply fill that missing observation with the previous one. And so we can also rebuild the 24-hour time series without the 25th hour and the 24-hour. We could even leave it to missing, but we can input it this way. I mean, inputting that hour this way is reasonable. Closer, especially in the night, closer hours have pretty close demand, so it's reasonable. So how we can do that? We can actually we could even put it here before storing. So what I want to do is fill. You can use the function fill. The variable we want to fill, it's called H24, and the direction, you see that there's an argument called dot direction. We want to look up. So look up is the previous value. Why do I do that? I mean, it's very not. I could have taken the last one. I could have taken the average of the two, but taking the last value is more honest because you already know that. Okay, if you're predicting, you should not take things from the future. Okay, that's like a general rule. But anyway, it doesn't really change much. But anyway, when we will work on models in state space forms, or starting from next week, we will see that modeling state space form can manage missing observations in a natural way. So there is no need when we work with modeling state space form to impute missing observation. Missing observations are legit observations, okay? And they will be treated optimally, okay? And so actually, while working with state space form, we will learn a way to impute, using the state space form, missing observation in an optimal way, meaning that your imputation is perfectly coherent with the rest of your model. So while in general you've learned, I impute missing observation and then I look for a model, or machine learning model. Well, if you have model in state space form, I mean, the missing observation imputation is done by the same tools that uses the model, and of course they will be neutral with respect to the model. So the missing observation, the imputation will be optimal with respect to the model, and they will be neutral in the estimation of the model. So but we will see that later anyway. But this to tell you, in time series analysis, actually we have a very strong tool to deal with missing observation. But now let's just replace it in this way. Okay, actually, I could like go back and rebuild the 24 hours data set. So the original data set, maybe I can still call it WDT. Again, let's go in the right direction. So I want to rebuild the hourly time series, which is now full. Okay. So first of all, I don't want to select the 25th hours. I don't want that hour. So in the tidyverse world, you can select variables in this way, but you can also deselect variables in this way. So minus and the name of the variable. And notice that actually we are used to use strings in functions that have to do with names. In the tidyverse world, you can directly use the words, the names, without making strings out of them. So it's full of interesting things. So this takes this data set and just select all the variables, but variable H25, which anyway is always missing, but 1 day per year. And then we want to go back from pivots wider, actually to pivot longer. Pivot longer. So now we yes, pivot longer is always more tricky in my head. Go to an example. So which column we want to pivot longer from H1 to H24. This is another way, very cool way to select variables. And we can also decide what we're going to do is going back. So names 2 will be now hour, and values 2 will be now, well, load. We can call it load again, okay? And of course, we assign it to a, so for example, the old data set that actually was not usable because of the missing data. And actually was missing data that was not missing, meaning that there was not NA, okay? And it worked, it seems at least that it worked. Okay. So we went back to, of course, now it's called H1, H2, and not just 1, 2, 3, 4. And that's a problem when we have to transform that into a date. Yeah. Okay, let's try to see how the. Yeah, we already did some good consideration about the various seasonalities. So I should see probably the seasonalities also in the autocorrelation function. I want to show you that as well. So for example, let's just run the ACF on WDT load. And let's just pick 168 hours. So, well, this is very eloquent. We see that there is this 24, again, the same thing. We see that there is a 24 hours pattern. So we have peaks every 24 hours. And they tend to go down, but then they go up. Because 168 hours is exactly 1 week. So from here, we see there is a 24-hour seasonality, but we also recognize the importance of 1 week because of 168 is 1 week hours. We could also notice that by, for example, taking the differentiation, so maybe let's just go with the pipe. It's more clear with the pipe. So we pass WT dollar load to whatever pipe you want to use, to ACF, actually to diff, and we take a difference, a seasonal difference every 24 hours, and then we look at the ACF with 168 lags, okay? So this is the load. I take the seasonal difference every 24 hours. So I kind of kill the seasonality every 24 hours. So this should make the other seasonality, which in this case is the weekly seasonality, clearer, more. And we see it from here. Now it's the peak is much more clear. Okay. I could have make it longer than 168. Maybe we can do it like 4 weeks. Let's look at 4 weeks. We clearly see these peaks every 168 observation. So every week we have a strong signal. So we see it from here. What about the within year seasonality? That would happen every 8,000. Okay, if it's 365 days, in terms of hours, it's 8,760. So let's take something larger than that, 8,760 number, to see if we also can see some within year seasonality. Because if I take the difference at 100, let's start just with this view. So let's take like 900 lags. No, 9,000, sorry, 9,000. Okay, here you see it's not that clear, that strong. I mean, it looks like around here, so around 1 year is going up again, but we don't see it very clearly, okay? So how can I see it more clear? Well, I can take the seasonal difference at lag 168. If I take a seasonal difference at lag 168, I kill both the within day seasonality and the within week seasonality, okay? So, and that should make more evident, if there is, of course, the seasonality every year. So let's just copy and paste this one and put, instead of 24, I put 168. So 1 week in terms of hours. And now it's much more clear. Okay? Actually, there is a very strong within year seasonality. The problem is that the other seasonalities are masking. So it's like the stronger seasonal movements are kind of masking the weaker seasonal movements. But it's not that they're not there. They're there. They're just kind of masked. And here we see clearly the effect. This is probably around this 8,760. It's a little more, or because we have every 4 years a leap year. But anyway, it's very clear we have also this kind of seasonality. So this is a simple way to kind of make clear that you have this kind of seasonalities. I mean, we already came to the same conclusion by a little bit by looking at the time series, a little bit about reasoning on the time series, which we know what kind of data it represents, but actually also just with these graphical representations, you would notice that. And of course, as I told you, there's also another tool which I didn't explain you. It's called Spectrum. Yeah, another tool would be this one, but I didn't explain you much how this works. This is called the spectrum. And in some way, you can also derive the presence of seasonality from here, but maybe I'll explain you how to look at this later. But this is just another plot we can use for. It's just a transform. You can see it as a transformation either of the original time series or of the autocorrect one. And it decomposes the time series in the variance explained by different sinusoidal component at different frequencies. Okay. Maybe I'll spend some time later on this. Anyway. So first of all, I would start with let's just pick up 1 hour and work on that hour just to find the daily model, of course, from the ARIMA class. But as I told you at the end of last lesson, the ARIMA class can be made richer using also regressors, okay? And so my basic idea is, okay, the ARIMA allow us most of the ARIMA functions in software around the world just allow you for one seasonal period, okay? There are some exceptions. For example, SAS, I don't know if you ever used SAS. SAS has an excellent ARIMA procedure, because in SAS they're called proc procedures. And in SAS, you could have an arbitrary number of seasonal flags, okay? But for example, in R, in Python, in the standard library, we don't have that, okay? So we can just deal with one seasonal delay or lag, whatever you want to call it. And then in this case, of course, if I work with daily data, the seasonal delay I work with is just 1 week, so 7 days. But of course, then we have to find a way to deal with within ear seasonality, which is there, okay? And of course, we will use sinusoids. I showed you already using the Shiny apps that I made, that we can deal with pretty positively with as low seasonality as the within ear seasonality, just using few sinusoids, okay? So let's start with the daily. So let's go back to the ICF. So pick up what hour you want to work on. Any preference? So it's 5. So let's take 5 in. So 17. Let's just call it Y, so it's simpler. So we steal it from, it's called DT24, it's H5, okay? This is going to be our time series. Sorry, not 5, 17, we said 17. Okay, so this is our time series. Of course, it's not technically a time series, so if we want a line plot, we have to insist for that. Of course, it's very messy because it's very long. Of course, there's also the COVID time, but it's there. I mean, we could even work on a subset of this data. I mean, it's a long time series. Maybe it could be also a good idea to work on a subset of it, but let's just work on all data up from now on. So let's look at the ACF of this actually can also, let's call also the library forecast, which has some good functions to work with. For example, the large ACF. So for example, now 7 days is 1 week, so this is daily. So we could look, if you want to look about, I don't know, 1 month, would be something like about 30 observations. And of course, we can also produce the PACF. Okay, here, what is clear is of course, we have some memory in the short run, which is fine. It just telling you, okay, the value of today is similar to all the value of yesterday. Good. But then we have these peaks every 7 observations. Very strong peaks. And of course, especially here, we see it here as well, okay? So we have a strongly seasonal time series every 7 days. So if you go into my flow chart of the Box-Jenkins, or my interpretation of Box-Jenkins methodology, this, okay, we didn't look at the stationarity invariance. So actually, the first thing to look at is stationarity invariance. We didn't. Let's take a look at about it. So we can, for example, produce. We could produce the means and the standard deviation every 7 days. So how do we generate the 7 days? Well, we can just there are more ways to do that. Probably the simplest way is just to build something that counts, so a sequence that counts from no, it's simpler than that. Let's just steal the name of the date from the date. So first of all, we have to create a date. We already have it, but it's not a date. So the date is actually in the T24 date, but formally it's not a date, it's just a number. So an integer number, but we have lubridate, which can change it into a date. So we can use year, month, day, transform that into a, sorry. In order to use the pipe, of course, I have to call the sequence of operation I want to do in the right way. So I transform that into strings, a vector of strings, and then I pass this, and this should work. Then I want, this is just the date, of course. Oops. Okay, it worked. It's a date. Now we have to steal the name of the, so we can call VUDAY. So it's actually also a function or so what's VUDAY now? VUDAY is a vector of strings, or actually a vector of numbers. So if you prefer string, you can have the string, I think. So here's label false. If you want the name of the day, you can just put label to true. And I think you will have the name of the days in the same language as your. There's a problem here. It's just a warning. You see, I have an Italian because I have an Italian installation. Okay. Again, you can choose which locale you want to have. If the number starts on Monday or on Sunday and so on. Anyway, it doesn't really matter because we want just to produce means and standard deviations, okay? So now we can produce the means by applying a tapply function to our time series, and we use the name of the week. Actually, I did a very stupid thing. That's not what I wanted to have. Actually, I want to take, sorry. Well, this is something you learn, but it's not right for what we wanted to do. We want to produce a mean every week and a standard deviation every week. So sorry about that. I did the wrong thing. Actually, I needed a counter of the name of the week. So actually, we should build like a counter that increments by 1 every 7 days. Okay. So sorry about that. It's simple. It's simple. So sorry about. I mean, it's good to know how to make that. So actually, we can go this way. So this is like the number of the week. We can repeat, and then we pass number that goes from 1 to the ceiling, I would say, our ceiling actually, of the number, the length of the time series divided by 7. So, okay, what does this thing do? So here we have a number that goes from 1 to approximately the number of weeks that we have in the sample, because I just divide the length of the sample by 7. So this gives us the number of weeks. If this is not divisible by 7, I take the integer which is larger than, okay? The first integer that is larger than that. And here, each equal to 7 means every single value here is repeated 7 times. So I get 1, 1, 1, 1, 7 times. So 2, 2, 2, 2, 7 times. So this is what we needed actually. And then we have to be sure that we build something as long as the y variable. But that is very simple to assure because we can just pick from the first to the length of y observation in this vector, okay? Okay? So 7 times 1, 7 times 2, and so on. And the length is equal to the length of the time series because of this thing. By using the ceiling here, I'm sure I built something that is at least as long as the time series. Okay? It could be longer, so I can cut it down if it's too long. Good. Now we're finally able to build our means using tapply, for example. Which is so y and a week and week. And we can do the same thing with the standard deviations. And we apply, oh, sorry, I didn't write the function. I don't know what function, it probably takes the mean. Okay. Okay, this is the so-called box-Cox plot. We could even fit a linear prediction, but it's clearly increasing pretty much linearly. Of course, it's very messy, but it's kind of linear. So I would say we should work on log. Suppose there is a, I mean, this is a low time series, so it doesn't happen. But for example, for prices, it could happen. Or for example, in the time series I gave you to do the prediction, not to do the hackathon or whatever, there are some zeros. How do you manage the zeros? Of course, you cannot take the log of zeros. How do you do the log transform with zeros?
We had that small.
Yeah, well, you can add a small number. What small number? My suggestion is try some numbers and see what is the value that makes the distribution after the log the more symmetric. Okay? So you can play around. Don't put it too small, because then you have very huge modulus number, negative number. So if you put 0.0001 and then you take the log, then you have minus, I don't know, millions and millions. And it's not a nice number to work with. So a good balance in order to make your distribution symmetric usually is a good choice of that number. Anyway, for we want to just do prediction, so it doesn't really matter. Of course, it's important when you do the prediction, you take the expectation that you have to add that small quantity that you took off at the beginning, and you have to take off the quantity you added at the beginning. Okay, and this does ensure that all your values will be positive. That's it. So if you also get a negative number, just cut them to 0. Okay. But anyway, so that's the solution. I would go with the log. Log seems to be the right decision, so we can produce Ly, which is just the log of y. Well, we already know the ACF and the PSCF of this. It's, of course, necessary to work on the seasonal difference, because it's clearly a time series with a strong seasonality. These are just the first 30 observations, but the seasonality is very clear, okay? And of course, we have this problem with the beginning of the year. Good, so let's look at how it looks like the ACF and PACF of the first seasonal difference here, okay? So we can like pass Ly to a difference every 7 days. And then let's just, for example, compute. Well, maybe we should store somewhere, for example. So let's look at the autocorrelation function now, which is much better as far as the seasonal delay, the seasonal lag is concerned. I mean, there is still something here, but not as strong as before. And I would say it's pretty much clear what kind of component, what kind of seasonal component we have to put. You see that you have a seasonal delay here. So here the season is every 7 days, okay? So, okay, we have something here. This is, I'm sure there is an auto-regressive model that is taking account of this thing here. But look at this. This is very evident. It comes out of this, and it's a delay 7. And if you look at the PSCF, this come out at 7, 14, 21, and so on. So we have a clear picture of a seasonal MA1, okay? This is very like handbook days, okay? It's very clear. Here we have a seasonal MA1. Remember, I told you when we take a difference, usually the need of the same delay for the MA comes out, and this is what is happening here. So this is of course important. Then let's look at the lower legs. So this going to zero slowly is of course something that is talking about an autoregressive process. What other, maybe 3, could be a good starting point, the autoregressive of order 3. So up to now, what kind of decision we have taken? Log, seasonal difference, seasonal MA, AR3. Okay. Let's try it. Could have you done these things by, I mean, the description about doing these things we did in the last 2 or 3 lessons, okay? Of course, you need some habits to do that, to be used to it. But at the end of the day, we're applying the algorithm that I put into that page of my book, the Box-Jackson algorithm. In here, we recognize 2 things. I'm not saying this is the final model, as I told you. We see in the first place what's evident in this ACF and partial ACF. We put that in the model, and maybe something is left, and then we try to add other components later, okay? So the next step would be like to start with a tentative model. So it's a RIMA. The time series, okay, here the time series, why? Because we have the lambda, okay? So here we will say that the log is taken by defining the lambda equal to 0, okay? Then we have the order, which is 3, 0, 0. So this is the non-seasonal part. And then we have to write the seasonal part. In this case, the function doesn't know what's the seasonal frequency here because it's not defined as a TS object. It's just a vector in our case, okay? So I'm afraid the help of the large A RIMA function is not telling you how to work that. But if you could look at the small ARIMA 1, so this is the description on how to deal with the seasonal part. So we define the period so it's 7, because we have our seasonality is every 7 days. And we want the order to be 1 and 1. Do you know what this means, this L here? In R, it's a way to tell the interpreter that is an integer number. I don't know why. Oh, you're right. It's a long integer number. So it's just to force that. It doesn't really matter. In some situations, it's more efficient. But you can just keep it. Then what else? We can leave a possible drift, or so a possible constant. So if you remember, going back to the RIMA, so there's either include drift or include constant. Here is a drift because we have a difference here, okay? But we can leave with include constant. Probably the constant would be slightly negative. Why slightly negative? Because we saw that actually in the long run, the time series was going down, not very strongly. Maybe it will not be significant because it was very soft, the downturn. One thing, last time I told you it could be a good idea to say that the method of estimation is CSS when you have a lot of data. Okay. I mean, this is probably not that, the model is also not that complex, so probably maximum likelihood would work as well. But when we have a lot of observations, least square and maximal likelihood are just equivalent. So they're asymptotically equivalent, meaning that for many observations, we get the same answer. And this makes us save a lot of computation time, okay? Indeed. So this is our first model. Maybe we can ask for a summary. Sorry, I mixed with the two pipes. You pick whatever pipe you want. So let's see. So actually the drift is virtually zero. As I told you. Yeah, probably negative, but very close to zero is probably zero. So these are all, I would say, significant, and this is even also large. And these are also in sample, like training error measures, so mean error, root mean square, and so on. But anyway, the important thing here is to check how the residuals look like, okay? So let's produce the ACF of the model residuals, which you can get out this way, or there's also a general function called the residuals. You can pick whatever you prefer. Again, you can use the pipe or like the matryoshka of functions, whatever you like the best. I'm mixing all things anyway. Okay, of course, this is not that clean. We have something here, also something here. It would be very hard for this kind of time series to have a so clean residual autocorrelation and partial autocorrelation function. On real data of this kind, it's kind of difficult. And still, we're missing one very important thing that maybe we can again see by looking at the ACF and PACF every 366, let's say, observations. So let's make this a little bit longer. Now you clearly see it. So the most important feature we're missing is really, okay, there's something here. We can fix that by maybe we can make a larger autoregressive or larger ANA. Let's try later to fix that if we have to. But the most important feature that we're missing is the within year seasonality, okay? The annual seasonality. And of course, one solution could be, okay, I could use like a yearly seasonal difference. Like I take this observation minus the same observation of 1 year ago. Yeah, you're losing a lot of observation. You're losing 1 year observation. Of course, this time series is very long, so it's not a problem. But of course, in that case, you have to find something else to manage the every 7 days seasonality, because 365 or 366 is not divisible by 7. So you solve one problem, but you create another one. And in some way, usually it's much better to work the way we're working. So work with a ARIMA model whose seasonal frequency is 7, and then try to fit, as I already told you, the within year seasonality using regressors. In particular, here, sinusoids are a good solution, okay? And so we'll go to the reg-ARIMA or ARIMAX model, so an ARIMA model with regressors. And in this case, we have to build our regressors. How many regressors? Well, it depends on how smooth is the seasonal component here. like Nordic data today, we don't have our Danish student. In Nordic data, they have a very slight seasonal movement due to, of course, the different use according to the lights and to the heating system. So if you have like Nordic data, maybe the first three sinusoids are enough to fit the seasonality. In Italian data, we need many, or we either need many sinusoids, like in my experience, about 15 would be a good choice, because we have this August that jumps down. Sinusoids, as I told you, are very good for smooth things, but when we have unsmooth things like August is really something that goes down rapidly. But also the winter vacation are kind of. So we could either use many sinusoids or also use a mixture of sinusoids and dummy variables. So like use some sinusoids for the, let's say, atmospheric or sun-related part of the seasonality, and then maybe build like a dummy from the first weekend of August to the last weekend of August, for example. Let's say is one. So we could mix the two things, okay? Let's start just with the sinusoids. Let's build maybe 15 sinusoids. What's the frequency of these sinusoids? Well, the frequency of the sinusoid should be 1 year in daily data. And what's 1 year in daily data? Well, this is something nice we can make also with sinusoids, and we cannot make with other objects. So a non-integer frequency is acceptable for the sinusoid's point of view. So actually 1 year on the average is 365.25 days, right? Because we have every 4 years we have 1 more day, okay? Okay, there are also small changes in how many seconds. That's not going to be evident in our time series, but anyway. So actually we could build our sinusoid, like our frequencies will be 2 pi divided by 365.25. I mean, it doesn't really change much if you leave 365, but anyway. And then times j and times t, of course. And j, as I told you, we can take maybe 15 sinusoids, okay? In my experience, it's good. Of course, you could analyze that using, I don't know, like BIC or Akaike criterion or cross-validation if you're patient enough to do that. There are many ways to decide. You can take this as a tuning parameter in some way. Or you can put many of them and just test for the significance. That's another way, okay? Or you can use lasso. I don't know if you ever use lasso, but I don't have any function that does ARIMA and lasso. So lasso, have you ever seen lasso? You're a statistician, so you don't count. You know what lasso is? Yeah, lasso. Okay. So of course we could use that as well, but at the moment we have no ARIMA with lasso. So we could write that function, but at the moment we don't have. But of course you could use it with lasso. Anyway, let's start building. So 15 sines and 15 cosines with these frequencies, okay? Of course, we could build a function to do this, but anyway. We did actually once. I think once I wrote a function to generate the sine and cosines. Well, anyway, it's not that big deal. So our frequency times t, as we already saw, we can use the outer. So the time will be something that counts from 1 to the length of the time series. Why? And we say 15 sinusoids could be enough. So let's build from 1 to 15. times 2 times pi times, or divided actually 365.25. Okay. So is that clear what I'm doing? That this is exactly what we did for monthly data. So I created, so this is going to be a vector that counts from 1 to the length of the time series. So this is the time, okay? And this is something that counts from 1 to 15. And then we have 2 pi divided by 364. Okay? And then, of course, we build cosines and sines, and we put everything in the same. Well, we could put everything in the same data set. So we could build a data set where we put the y variable and all these frequencies or these sinusoids. For example, we can call this TS data. We build a data frame, and here we put y. Here, actually, well, we can just, let's see how it reacts. I think it generates automatic names here. So the cosine of frec t, this is a matrix, the sine of frec t. Let's see if it, maybe we should change the names. Oops, I didn't. Okay. Let's explore it. Yeah, it's fine. It just used the name x1, x2, x. Maybe we should change that into more intuitive names. So we can just rename them. So the first one, we just leave y, and then actually it's the original y, and then we can like paste 0 cos from 1 to 15, and then paste 0 sine from 1 to 15. Okay. So now the names should be nice. Yep. Or I think I wrote 5 instead of 15. Yeah, right. Yeah, no, it's fine. Why is it fine to have speaking names? But well, because if we want to test what is significant or not, it's more recognizable. Anyway, so how does this work? So this would be our model 2. So ARIMA, well, actually, we can copy this thing here and then just add the regressors. One thing I would pretend that maybe we don't know the last 30 observations so that we can predict them, okay? So let's just maybe throw away the last 30 observation. We can do, I don't remember, there was a simple way to keep like, no. Yeah, this works. Okay, for example, for throwing away the last 5 observations, you can use head with a negative number. It's easier than 1 at 2. Okay.
Or tail.
Yeah, tail. I want to throw away the last many observations.
Yeah.
If you do this using the tail, you are throwing away the first ones. If
Yes,
you put
yes.
-1. Okay. So we could like go ahead, and here we put minus 30. And now we have to add a xrec variable, which we have, which I'm not sure if we want a data frame or no, actually it wants a matrix. It should not be a data frame. Good. So I built a data frame, but it was useless. It's every function has its own tastes. It doesn't really matter. We can fix it. We can go as data, as a matrix, sorry. And we pick, so from TS data, so we, first of all, we have to throw away the first variable, which is the Y. And then we can, I think we can apply the same head game here. I think it should work. Let's see. No, it's not working. Ah, there's a comma missing, sorry. But still is not working. Ah, okay, sorry. Okay, great. Okay, estimated. So the drift is still, well, I could have thrown away the drift. Well, we will put this to false, but anyway, it's 0 really. Everything seems pretty much significant. And let's look at the residuals, the autocorrelation function of the residuals. So actually, receipt does the same thing. They're like a renaming of the same function. And SEF. Let's look at the long period, so 366. I mean, there's still a lot there. So we're not cleaning up everything here. Actually, we're not cleaning up almost nothing. Strange, though. Hmm? I don't know, more sinusoids. Is fine. Yeah, it was fine because in the summary we had the right variables. So. I don't know. We can either add more sinusoids or try to add like dummy variables for the two main vacation periods, so the winter vacations and the summer vacation. Let's make it simple for now because we don't have time to be more precise. Let's maybe build a dummy variable that it goes to 1 from, I would say, the 22nd of December to the 6th of January, and then do the same thing with the whole August. That's simpler to manage, okay? So let's go ahead and try to model this seasonality in this other way. So we could, how do we manage that? For example, we can call this the, in TS data, we can call this, for example, winter. So more explicit than so it's not possible. How do we generate that? It's not as simple because using like SQL logic or something like that. So we want to generate something that is one between. I mean, it's between 1 year and the next year. Well, actually, it is simple. It must be either larger than the 25th of December or the 22nd of December, or smaller than the 6th of January. So actually, it's not that complicated. So sorry, let's use the tidyverse tools. So we say we want the winter vacation, and so this is true if although we don't have a date here, though. That's too bad. But we have a date in the other data set, which is called, in this one we have a date. It's a proper date. So we can use, let's see if it works just with the string, I'm not sure. The problem that we have to get rid of the year. So month must be 12, and so it's kind of more tricky. Let's make it so. I think this should work. There's a function to extract the month. Let's see if, I think it's just a number. Let's see the format of this date. Okay, this is not a date, even worse. First of all, let's transform the date into a date. So here we can go with simple R without using. And we can just go with as date. Okay. The problem is that we have to specify the format. Or you could, no, we could use the other way, so it's simpler. We could use the other function, the one that I showed you before. So it would be year, month, day. I think it should be able to recognize it. Yes. And now we have a date, a real date object, okay? And finally, we can use it here to to extract the month. This should work now because it's a proper date, right? So the month must be large, must be equal 12, and we can do, and or we can do the product, which is the same thing in this case. And the day of the month, I'm not sure. Yeah, there is M day. Yes, it's working. Yeah, it's worked. Great. And so the month day, let's say greater or equal to 22, okay? So this is 1 in that case, but it should be 1 also in another case. We can add. So, oops. So the month is equal to 1 and M day is smaller or equal than 6. Okay, this should work. Let's just view it before save it in some variables. What's the problem? What's the problem with this? Non gli piace questo. Ah, sorry, sì, non ho messo questa è una funzione, ovviamente devo applicarlo. So this is a function, I have to apply this to the data set, of course. So now it should work. Okay. It seems to work. So it starts with 1, and then, of course, it should go to, disappeared? Ah, here. So let's see the dates. Ah, the dates are not here. Okay. Let's just assume it's working. Okay. Okay, this is just winter vacation, but we need also summer vacation. Well, summer vacation is easier because we said we just keep the August as summer vacation. So we can add another variable here. So summer vacation, and in this case we just keep month of the 324 date is equal 8. So this is going to be logic. We can go with as numeric. Here it transformed automatically in numeric because I did product and sum, so I didn't have to transform the true and false into a numeric thing. Here I just have a logical thing, so if I don't transform it to numeric, I would have a true and false, which would work anyway also in the regression, but maybe it's more elegant to transform it to a number. And we can overwrite the data set, okay? Good, so let's try again. We can just copy the last model and adapt. So what we changed is just this one, but this is good as well. I mean, we don't have to add any other information because we changed the TS data, so it's fine. We can just throw away the constant. So we saw it's always equal to 0. It's really irrelevant. Okay. So it looks like it's It's not there. Strange. Ah, because I changed the name. Now it's called it. Okay, sorry. I called it TS date, not TS data. So I was stupid, but I understood why I was stupid. And that's already a good thing. Good. Fine. Of course, this is strange because this is negative as expected. Summer vacation is positive. That's strange, you know? And actually not very significant because this is just about the double of that. It's more than the double, actually. Anyway, let's see if the residuals look better now. And actually, I'm not able to kill that thing here. It's really hard to win that. I mean, in some ways, it's strange what is happening because these numbers are strange. But anyway, let's try to do the prediction of the last 30 days, and then we can stop here, of course. So actually, it would be sufficient to go with forecast. So this is a RIMA. So the function we want to look at the help of is forecast dot RIMA, which is here. What about xreg is here? Okay. So we can. So we pass the model. Actually, maybe there was also a subset here or not. No, there was no subset here. And then we just pass the xreg. Xreg will be the tail of this. And it will be the last 30 observations. I call it forecast trip because it's the third model. So just let's hope that it works. And it does work. Okay, didn't transform it into a matrix. For some reason, it doesn't like data frames. Okay, worked. I think the plot, in this case, maybe autoplot will make a nice plot of this. Okay, it's a kind of squeezed out. But anyway, it would be nice to just maybe compare the forecast to the real data. So we can just like plot from the forecast, we can plot the so-called mean, which is the mean, which is the prediction. Oops. And then let's just plot the last few 30, so the tail of y, 30 observations, which is that so bad that it doesn't show? It's just because okay, look at the number. The forecast has kept the index of the new variables. So sorry about that. I think we can get rid of that just by doing this. Right. Okay. Not too bad. Okay. Of course, the within year seasonality in so short forecast is not that important. So we would notice the need of the within year seasonality when we have longer predictions, okay? Because in the very short run, anyway, the system adapts because it works on the difference with respect to the last week. So the last week, if the last week was high, then also new week tends to be high, okay? So the need for this long range seasonality, smooth seasonality, we would see better in the long run. And here there's of course a problem, clearly. So our first forecast would be, I don't remember what days was that. Probably there is a reason. We could just, probably I don't remember the name of the data set I created. So the T24. So I guess we're predicting probably the 2nd of May. Strange. If it was the 1st of May, I would understand. I would have understood. So actually, sorry, the forecasts are the red one, and the real value is the black one. So we are under forecasting the first observation, which is the 2nd of May. This is strange. I don't know a reason for that. Wait, this is I have no idea. I have to think about it. System. Anyway, the rest is good. Yeah, one has to think why this is strange. I mean, it's the 2nd of course, it probably has to do with the 1st of May, which was the day before.
But maybe because it was festive.
I see the 1st of May, but this is the 2nd of May, which is not festive. Oh. Good. We have to think about it. Anyway, this is, of course, we would need to do more checks and so on. It's strange that, for example, August received a positive number. But anyway, this is basically a decent model for the daily time series. Maybe on Monday we try to go straight on the hourly data, which is more complex. But still, we can use similar tools and then compare the prediction. Of course, this is just 1 hour. We would have to make 24 models for this, but having time, we can do it. We stop here, and so we see you on Monday. Of course, using my app, it would be much quicker to do all this reasoning. I have to add probably something to automatically generate the sinusoids. That would be useful, because at the moment you can import regressors, but you can't. You have to import them from the outside. Va bene. So,